So once again, I'll be talking a little bit about what seems to be a much more education-focused aspect of the work that relative to the work that we've seen by the previous speakers. And so what I'm going to talk about is our participation in the Solar Decathlon and the engineering perspectives behind it. So as you may or may not know, the Solar Decathlon is a contest that was initiated by the U.S. Department of Energy in 2002, and 8 competitions have taken place since. And we participated in 5 of those competitions, and 3 of them within the last 10 years. It's a competition that is focused on student teams, starting from basically zero, a clean sheet of paper, and working towards a full-size, fully built, proven solar-powered house, net zero house. And it's the Solar Decathlon, so there's 10 contests. The houses are judged by their architecture, market potential, engineering, communications, innovation, water, health and comfort, appliances, home life, and energy. And so you see that the green challenges are what are considered to be juried challenges, and the blue are actually measure challenges. So our houses are instrumented with Department of Energy instruments, and measurements are taken, and houses are assessed in that manner. So I'm not sure if this has a laser pointer, but regardless, let's see if I can, oh, okay. So what I'd like to point out is, so this the most recent U.S. Solar Decathlon took place in Denver, and this is a shot of the mall prior to the competition. Our house is located right here. We're next to UC Berkeley. The Swiss house is here. The Dutch house is here, and a few more houses are behind us, and so on. And so this is the nature of the competition. So that's the U.S. Decathlon, but what's obviously important is that there's the Solar Decathlon Africa, which is taking place here in Morocco in 2019, and so I hope that, our experiences are relevant to the experiences going forward for some of these decathlons. A number of European decathlons have taken place, including one next year. China, Latin America, and Middle East have also had or are planning 2 decathlons. So this is a competition that is growing worldwide and follows much of the same basic format of the U.S. Solar Decathlon. So as I said, what's important is that this is a student-led competition, and it's a competition where we start with absolutely nothing to start with. We started off, as I said, with a clean sheet of paper to give you some idea of the timeline of what we were facing. We were notified in January 2016 that we were one of the competing teams, Team Maryland. In that spring of that year, we went through our conceptual design phase, followed by the summer of the system and architecture design, subsystem and prototyping design, followed in the fall of that academic year. So that's one calendar year. And then in the following less than 1 calendar year, we went through prototype construction, construction integration, transport, and competition. And so the intensity of the level of activity was relatively uniform throughout the entire process. And I say that because even initially, even though we weren't doing any construction, it was important in the very beginning to try and put together a team of very heterogeneous students. One of the main things is what we found as a challenge here is this notion of the interface between engineering and architecture cultures, that we had many gaps to bridge in terms of our design ideas, approaches, and language that we use in order to express our design ideas. So initially, we're interested in doing functional design using the performance requirements that are set by the DOE Solar Decathlon Rules Committee. And then we go through the concept development phase to explore potential markets, innovation through systems integration, and the pragmatic constraints of cost and transportation. And so these are all absolutely crucial. And one of the things is I highlight systems integration because, of course, we're not allowed to use any technologies that we wouldn't be found in the home. So really, the technological challenge here is the integration of existing technologies in order to make them as efficient as possible. Okay? So our approach to the Solar Decathlon resulted in what we called our house as being REACT. So that's Resilient Adaptive Climate Technology. And so of some of the main technological features that we developed early on in the process. Oh, great. Okay, good. Thank you. So some of the main technological aspects of our project were that we had very strong integration between the courtyard and the court. Oops. Uh-oh. Now we have full control of our technology. So this is our conceptual design, and I'd like you to keep it in mind when we look at the actual house to see how closely our initial conceptual design ended up matching our final design. But this is the overall schematic of our house with our courtyard in the middle, our bedroom on one side, living room on the other side, kitchen over here, bathroom back here, and the core area that is vital to the integration of all the pieces of our house. So there was a significant amount of integration that we achieved through the management of thermal management between the attic and the courtyard area. What's important is the modular construction that made it possible to disassemble our house and transport it the nearly 2,700 kilometers between building it in College Park, Maryland, and competing in Denver, Colorado. We were able to design a system where we were able to sell and purchase power through battery charge and discharge of our house. We had strong integration between our heating, ventilation, and air conditioning and our energy recovery ventilator. And what was most important to tying everything together was this overall supervisory control system that we'll talk about for resource allocation. Now, I don't expect you to see what's taking place in this slide. It's a very busy slide, but I put it up intentionally because it gives you some idea of the magnitude of the engineering program that we were managing. We had work that was taking place in terms of power, HVAC, appliances, the core of the house, the courtyard of the house, living systems, water, automation, and systems engineering. And so these were all of the engineering aspects that we were working on, even though some of them sound like architectural aspects. This is giving you some idea of the size of our team of students that was working on the various engineering subsystems. So as our design proceeded, a number of design philosophies and concepts evolved from our initial design concepts through the implementation. And one of the most important concepts that we were following was this notion of disentangled design. And that is that if we are going to replace something, we don't want to have to tear down an entire wall or replace an expensive unit. And so the basic idea was to concentrate all of the mechanical systems in the core of our house, have a spine down the middle of the house that basically was the backbone of our house that included the wiring and the water lines. And having the core of the house interface with each one of the modules meant that we could place all of the interfaces on the core itself. So this interface engineering was crucial to our house. And so this is a picture of our ultimate realization of our house, and this is our control system computer, which is on the back end of the spine wall. So our mechanical room ultimately connects through the spine to the brain of our house. Okay? So as we integrated elements, integrated design, architecture, and elements, we ended up developing some unusual configurations for our house. So if we look at the HVAC system, we had a variable refrigerant flow heat pump system and a heat pump water system. And we were able to integrate them in a novel way that if we took the outdoor unit of the hot water heat pump and the outdoor unit of the HVAC system, under summertime conditions, we would draw cold air in from the outside, cool it down further before we sent it to our outdoor unit of our air conditioning system to improve its efficiency. And now, in summertime, what we would do, in wintertime, we would draw warm air from the courtyard through our attic, through the heat pump system, and dispel its hot, cool air out the one side and draw warm air in from our courtyard through our external unit of our HVAC system in order to maximize its efficiency. So this variable geometry and the coupling with our courtyard enabled us to achieve a higher level of efficiency using relatively standard equipment. And so this is ultimately the exhaust of this system up in our attic where it contains the two outdoor units. Our electrical system design appears to be relatively standard. We have 14 PV modules giving us a 10 kilowatt array. what we decided to ultimately work with are DC to DC inverters in order to optimize power and to keep the entire bus as a DC system in order to maximize efficiency and maximize flexibility. Okay. Water was important in our system, and so we had rain and gray water filtration, storage, and automated irrigation. And this work continues despite having the competition ended. I have a group of students that are also trying to bring both of the rain and gray water streams to potable standards through a relatively complex filtration and disinfectant system, which is ongoing work. So as you would imagine, a highly automated house would require a number of sensors and actuators. Because this was an educational project and because we wanted maximum flexibility, we decided to build our own sensors. We built them off of Arduino-based temperature, relative humidity, carbon dioxide, soil moisture controls. Each had a Wi-Fi shield and a web server, and you'll see why we chose this configuration. And so what we see is this is one of our Arduino relative humidity, our irrigation control of our green wall outside based on the moisture content of the soil. Actuators were also Arduino based for skylight and irrigation systems control. Okay? So to tie all of these things together, we put in a substantial effort into physically based modeling of our system. And once again, because this was an educational project and because we wanted maximum flexibility, we decided not to go with, for example, some of the off-the-shelf simulations that were described in the previous talk. We decided to develop them on our own. So we started off from scratch, developing solar radiance models that are valid worldwide at any time, the associated projection methods and adjustments for cloud cover, exterior energy wall balances, current versus voltage diode models to model the PV array. And what was important is that we also stored information about the behavior of the occupants, the characteristics of the PV modules, and a number of other factors in machine-readable XML formats to give us the most flexibility in terms of our ultimate dynamic simulations. So as an example of one of the simulation elements, I'm an engineer, so typically we have to show at least some equations in each of our presentations. We can consider PV module modeling and parameter identification. And so if we look at the back of the PV module and read off the maximum power conditions, maximum power voltage, maximum power current, short circuit current, and open circuit voltage, we can then identify all of the parameters of our diode model, including some regularization equations, which aren't critical to this talk, to ultimately be able to give us the current versus voltage and power versus voltage for any PV system under any lighting condition and under any temperature condition. So this gave us the maximum flexibility in terms of predicting our PV array performance. So how would we use this, for example, in our design phase? So here's an objective that what we would like to do is we'd like to determine the number of PV modules, the capacity of our battery system, and determine those against one another over the course of a year, given some nominal load profile, in order to determine how many PV modules and how much battery capacity we would need in order to achieve, say, nearly 100% performance of continuous power production, power availability for a standalone PV system as a function of our design characteristics for our system. Now, if we're thinking in terms of modeling in a broader sense, what our ultimate objective is to develop a flexible modular dynamic simulation framework that's suitable for design, optimization, and control applications. And arguably one of the most serious challenges to developing such a comprehensive model, in addition to being able to make sure that it's flexible, is the multi-scale nature of the systems that we're working with. And so if you start to think about the various timescales of systems that are powered by renewable resources, we have timescales which are relatively instantaneous. For example, how the PV array will react to changes in irradiance. We have timescales on the order of minutes that correspond to cloud passages and the activity of residents within the household. Hours characterize daily solar irradiance changes and the water processing dynamics of our system. in terms of dynamics that are measured in terms of days, major weather patterns. For example, here we see a storm moving in that reduces our irradiance over the course of a week. Weeks, seasons change over the course of weeks, green wall and other plant growth change as well. And years, home mechanical, electrical, and information technology evolution also should be considered as a time scale of the overall system because it ultimately affects the dynamics of our overall system. So as a major effort in our work, we put together a predictive dynamic simulation of our house. It was a 2-year effort marked with the development of about 20,000 lines of open source Python code. We have, as I said, we would represent nominal residence resource demands, PV label data, each house design characteristics into a machine-readable XML file. So I said this a couple of times, maybe the details are lost, but the point is that by doing it in a machine-readable form, we can basically design houses with different characteristics in a very quick way and characterize them under different conditions. So the way that our simulator would work is it works in an automated way. The simulator wakes up in the morning at 12:05, reads the local weather data at the local time of each one of our individual houses and predicts the dynamic behavior. And so this is ultimately what we find. So what we find is that from midnight to midnight, we have our PV power that's based on our irradiance model and our local weather data. We have fixed and movable loads that correspond to the behavior of the occupants. For example, this is car charging, this is hot water heating for morning activities, this is dinner activities, clothes washing, and so on and so forth. And ultimately, what we do is we integrate these powers in order to get the net energy balance for the day. And so what we see is that at the end of the day, we've ended up net positive in terms of energy. And so because we also have a rate schedule for the cost of buying and selling electricity, we can translate these dynamics into economic dynamics. So here we have an instantaneous profit, and here we have instantaneous losses. But once again, if we integrate those over the course of the day, we see that we make a small net profit of less than about $0.50 of a US dollar. But still, it's a profit, so that's fine. Because we didn't have the house to test our model, we had to go to a surrogate model. And so fortunately, we had a previous competition house on our campus, and we used it to test and validate our model. And so what you see here is you see an example. So this is the house that we used. It was for 2007, from a previous competition. And what we see is the predicted power generation, the actual measured power generation and the error, and even more impressively, the power use by occupants in terms of the predictions and the measured. And so, of course, occupants are much harder to predict than the physics of our planet. And so we would expect that the error that we see in terms of predicted power use would be less than the predicted power generation curves. So we take that information and then we try to quantify sustainability metrics. And so if we have all of the characteristics of the house over the course of the day, what we can do is we can define sustainability characteristics in terms of electrical energy sustainability, which is just the difference between PV power production and consumption integrated over the course of the day. Thermal energy sustainability, which basically measures how well we make use of the thermal energy that's available in the courtyard, either for heating or cooling applications. Water sustainability, so that's the normalized ratio of reclaimed filtered gray water to total use. And then reduced carbon, and when I say reduced carbon, I'm talking in a chemical sense. So based on the production of energy-rich carbon compounds by the indoor and outdoor gardens relative to the house occupants' CO2 production. So to control our system, we use this physically based model to develop this supervisory house resource allocation control system. And so the basic idea was that the control system that we build was not going to be invasive. We're trying to stay away from these highly interconnected systems. And so in the context of the supervisory control system, the main concept is that our control system transmits set points, and it doesn't interfere with low-level control loops like the HVAC thermostat. So this is good for fault tolerance and minimum invasiveness, maximum upgradability. So what this allowed us to do was to not so much control everything on a minute-to-minute basis, but basically provide information to the house occupants on what's the best way to optimize scheduling of renewable resources in our system. And so ultimately what we see is these web server sensor actuators, they allowed asynchronous queries of the house states and allowed us to tie all of these pieces together in a relatively seamless fashion. So putting those all together, what we ultimately put together was a front interface for the homeowner. And so what they would see on their monitor, their flat panel screen at the end of their hallway was this picture, and this indicates that we have 4 virtual houses running, one in College Park, Maryland, one in Wisconsin, here at the competition in Denver, and at the last Decathlon competition in Irvine, California. And basically what this summarizes, and you can actually, if you want to take your phone and go to reactvirtual.eng.umd.edu, you can actually see today's predictions of where things stand. So these are our sustainability metrics in terms of water, thermal energy, carbon, and water. And we see that if we go to College Park, things were pretty negative overall, but we had a high sustainability metric in terms of water for our system. So if we wanted to click on that and go a little bit deeper, once again, there's a lot going on here, but the basic idea here is that we're indicating on a day-by-day basis our sustainability metrics, and we saw that most of them were negative. We were down on power production. This is our courtyard energy balance. This is our home energy balance. This is our CO2 balance, which includes CO2 production by humans, CO2 consumption by plants, and CO2 balanced by the ERV system. And what's important is this is our water balance. And so what we saw is that the weather forecast had predicted that there was going to be a substantial storm coming in. And indeed, the day before we left, there was this large storm that was coming through to the East Coast. And this is why our sustainability metric for water was high relative to everything else. Costs were relatively poor, and so on and so forth. But the bottom line here is that we now have the ability to prompt the homeowner that we have normal battery charging, that we have a frost watch and a skylight watch as well in terms of manipulating the parameters of the house. Okay? We've been running this system for now almost 1.5 years, and so we've been accumulating sustainability data over the course of the year. So this is winter and this is summer, both in terms of profit and in net energy and all of the other metrics that we spoke of. And as we're starting to wrap up this talk, we get back to the actual physical project itself. So taking a quick look at the evolution of our house in terms of the physical space, this is the construction of the core. It was the only stick-assembled portion of our house. The rest of the house was composed of these structural insulating panels. So basically we went from this to nearly our complete house in one day because of the rapid construction that's possible with these SIPs. Here are some of our students. So once again, this is a student-led project, and these are 2 chemical engineering students standing on the roof installing the PV arrays. And this is now the disassembly of our house. So we're basically getting ready to put them on 5 flatbed trucks to ship them out to Denver. So we arrive in Denver, it's much colder, we start assembling our house, and this is ultimately our house as it's finished at the end with its interior showing that indeed we've realized a fully complete house. So one of the things that was really exciting about this competition is that this is the first time in the history of the Solar Decathlon that it ever snowed during the competition. So this threw the entire competition into a different mode than anybody had expected. And in my sense, it's fortunate that it happened because it highlights the capabilities of the control system that we designed. So this is our predicted performance during the course of the competition. It's an 8-day competition. It was from the 6th of October through the 13th of October. The dates don't quite match up because the competition was started at different times of day. But the bottom line here is that this is predicted performance of the house, and this is what the DOE measured in terms of our overall energy, net energy. So we started off with 0. We had a couple of promising sunny days where we were starting to be net positive in terms of energy production. We reached a peak where we were doing absolutely fantastically, and then our snowstorm came. And we lost 2 days of performance because we couldn't get up on the roof and clear off the modules, and so we basically lost everything that we gained. But we had a few more positive days afterwards, and so we were able to build up. And here's the key notion of the entire talk. If you go away with one idea, this is it. We were at the end of our competition, And our models would predict, you can't see them in this simulation because they don't, the simulations were prior to the actions that we took. But we had predicted far enough ahead that we would be able to generate enough power over the course of the next several days in order to be able to reach net zero. So what we decided to do was we decided to dump all of our main battery charge during the peak cost during the day in order to make as much money as possible. We completely drained our car battery, and then we bought as much electricity as possible in the middle of the night when it's cheap in order to get us back up. And once again, we then used our battery also in order to recharge our car fully in order to get us to net zero and maximum profitability at the end of the competition. So this is the power of the predictive models. They allow us to look into the future in order to be able to optimize our resources, and that's the basis of our overall control scheme, this notion of optimized resources. So here we're at the end. Outcomes and lessons learned. As far as I'm concerned, the best outcome is that we came in second, so we were behind the Swiss team, which had a very formidable house. They actually came with a community center and with a budget 4 times of what we did, so we don't feel bad losing to them because they had a spectacular house. But development of physically based modeling tools for quantitative comparison of design alternatives and systems integration was crucial to our success. Simulators elements transitioned directly into virtual React, making it possible to optimally optimize and schedule resources as we just saw. And just as in the first talk, talking about communities and clusters, we believe that some of our simulation technology would be scalable to the community level. And ultimately, the innovation success really depended on a strong collaboration between engineering and architecture students. Attention to code and transportation requirements were critical to this project. So anybody who's involved in the solar decathlon, keep in mind houses must be built to code, and you have to transport them to the competition site and back. And the transport cost for us was one of the major costs of our overall project. So with that, I'm going to stop. Thank you for your attention.